Hi, welcome back to the final 4 lectures of Introductory Astronomy. Exciting lecture today. We're going to go into the very beginning of the universe and speculate, well, take what data we have and try to figure out as best we can what might have happened in the very beginning from the perspective of astrophysics and astronomy. So this strange image around me, I guess as you're looking at the screen, it would be to the upper left of me, in my little bubble, is something that has something to do with the early universe, and we will get to that later this class. You can wonder what it is. Okay, first of the 2 obligatory slides. We have Introductory Astronomy right here and now. Beginning of the universe is now. Next time is more beginning of the universe, where we talk more about forces and inflation. Since we're coming back after a break, we actually have a lot of APODs to catch up on. So this is occurring at your local Michigan Technological University. I am Robert Nemiroff. If you want to take this class for credit, you need to go here. And most of the people who are in this class have never shown up. I have never seen them. Sometimes I walk past somebody on campus who looks at me as if they know me. And I don't know them because I've never seen them. Possibly that's just my own neuroses, but possibly they're in this class. I don't know. But you are responsible for these things. I put these in every time so people can't say I didn't know what I was responsible for, so you have to give me an A. Whatever logic whatever gives you that. But you're responsible for the lecture material, at least the part that's correct. I will list Wikipedia entries, no extra charge. In fact, in the no extra charge is really no extra charge because, as I've repeated several times, there is no textbook for this class. And generally, I've received positive feedback about that. I have not received negative textbook. Where's my book? Where's my book, dude? I haven't received one of those. I received several emails that it was kind of cool not to have a book. With that intimidation, who in the studio audience would rather have a textbook? Nobody. Okay, we're 0 for 4 here. So we'll be reviewing the APODs during the semester up until the last lecture. And I will review them. I'll review a whole bunch of them next time. So if you're taking the course for credit, you should have completed homeworks 1 through 12, homework quizzes 1 through 11, sorry. 12, which is the last quiz, will be released Wednesday at 4 p.m. There will be no homework 13 because that would coincide with the release of the final, and that's kind of strange. So we're just going to sort of incorporate that into the final. So the last 2 lectures you will be quizzed on, but will sort of be final quizzed on. So the final, I've determined, will be released not this coming Wednesday, but the next Wednesday, and due even the Wednesday after that. Okay, so it will be 100 questions. It will be online. So I don't know. Should be interesting. Hopefully it is. The Wikipedia entries which you might want to read up on are cosmological principle, perfect cosmological principle. This is sort of an outline for today's lecture. The Big Bang, cosmic microwave background radiation, which we've touched on a couple times, but we will go into today in some more detail. Let's kill the red stuff. Okay, so the universe and the beginning of the universe has been discussed in many societies. There's many universe creation myths. Many of them have to do with, they are old, very old, with the local farm animals, things like that. These are very interesting to study, not because modern Western society really believes them today, but because many times they say interesting things about the culture which created them. So in the modern era of telescopes and satellites, so we have a much, what we think is more scientific view of what the beginning of the universe is or was. And based on a lot of data, trying to understand that data and predicting what other observations would yield, many of which are spectacularly successful. Not all, and so that's the idea of science. Part of the idea of a scientific theory is to be predictive. So you have your theory, you predict something, and if your theory never predicts anything that comes true, then it's not really very useful. it might be useful for predictions. My view of physics is we are physicists, like me and other physicists, are a lot like psychics. We are psychics, except we don't make predictions about what people who would be married, who Liz Taylor would marry, or stuff like that. We make very strange, specific predictions about what different machines will do, what different measurements will be, in the lab, what stress things can take, things like that. Psychics generally, their prediction rates are not much better than someone who doesn't claim psychic ability, and this is tested with the last lecture will be pseudoscience, and so I'll really get into pseudoscience then. But please feel free anytime before starting the final to wait for a call from your psychic to call you and tell you the answers to the final. Please don't, you can't talk to anyone during the final because they might know specific things. But please, if you have a psychic, please think about them now and have them call you and volunteer to you the answers to the final. That'll be fine, okay? But you might have to hang up before the actual final starts. You start it online, and then remembering those. And the impressive thing about this is that as with all the quizzes, the orders of the questions on the final will be randomized by the computer. So if they're able to call out the A's, B's, and C's, and D's and get you 100% well before you even begin, even more impressive. Sadly, no test like that has ever been passed to satisfaction by any psychic. However, because their predictions aren't much better than someone who doesn't know. It could be a little better because sometimes if they look at somebody, some psychics are actually very well schooled at looking at people and knowing what kind of people they're dealing with more than the average person. But don't let that fool you. As I said, physicists, though, and many scientists can predict things, but they don't predict interesting things that would be interesting sociological things. They predict very specific things. Which is useful. So in this modern era, sorry for the divergence, we have theories of the universe that create possible predictions for what other things you might expect from the universe. If this theory of the universe is right, then you might go out and see this with your telescope, or you might find this in the lab. And so, but even then, scientific theories, some make predictions that don't come true, and they are either modified or discarded. That's the whole idea of science. And so one of the early ideas of the beginning of the universe, one of the early modern scientific ideas, so we have, is the steady-state universe. So this has now been discredited, but the steady-state universe is sort of based on the perfect cosmological principle. The perfect cosmological principle says that the universe is pretty much the way it is when we look out at the universe, and was always this way. So it didn't matter what year it was, whether the sun was just formed, whether it was 10 billion years ago or 100 billion years from now. The universe always pretty much looks the same. Now, there's not the same galaxies. There wouldn't be the Andromeda galaxy or things like that. There would be another galaxy there as things change, but the gross attributes would be the same. So, for instance, every year there's a different astronomy class. But pretty much the students have roughly the same height distribution, roughly the same grade distribution. Many times ask some of the same questions. So if that was true all the way into the past and always into the future, then that would be like the perfect cosmological principle. Whereas if the cosmological principle was true, then in the first year of astronomy class, you would have all babies. And the next year we'd have toddlers, and then every year they would grow older, and eventually we'd have astronomy classes with just old people with gray hair. Okay. So the perfect cosmological principle says they're always going to be the same. And the universe does not evolve with time and looks the same in every direction. The Big Bang universe, so the steady-state universe has made predictions that didn't come true, but there are some people, a very, very small fraction of the astronomical community still believes in a steady-state universe. A very small fraction. It has not made predictions that have come true, and some of the predictions of the Big Bang universe, which incorporates the cosmological principle, have come true. So we sort of have a winner in terms of which has the greater predictive power. So the Big Bang universe, which says the universe is expanding, Again, some evidence for that is that all galaxies, not most galaxies that we see, the further away the galaxy that we see, the greater the redshift on the average. So in this universe, the universe says that evolves in time, but it looks the same pretty much in every direction. Little slight differences because we don't have the same galaxies in every direction, but pretty much it doesn't matter where you are in the universe. So it doesn't matter where you are in the classroom. If you have a classroom with lots of people in it, let's say all toddlers, you could be one of the toddlers. You look around, all the toddlers look pretty much the same. If you're an old person, in an old person classroom, you look around, they're all old. So it's the same in every direction, in every location. Okay, so one of the predictions of the Big Bang universe then was dramatically made by a couple people, including Peebles at Princeton and Gamow, who said that, look, if there was this Big Bang early on, then the universe is much hotter in the past. And some people said, well, yeah. And so if this universe is much hotter in the past and a universe is dark now, that means the photons can pretty much fly free through the universe. Now, if it was much hotter in the past, then there would, at some point, it was just so hot, photons couldn't fly free, so we should be able to see back to this last scattering surface from when the universe was relatively hot to when the universe cooled to when it's not so hot. We should be able to see back to that and today. And that should be at about in the microwave region today, if we can estimate correctly. And so when that prediction was made, people thought that it would be very tough to go out and verify that prediction. But still, it's really good, because it shows a good science theory has clear predictions. So the Big Bang now has a clear prediction, and the steady state people who were battling it out at the time did not think that. So this is actually past the Curtis-Shapley debates, where it was found that the spiral galaxies were lots of other, spiral nebulae were lots of other galaxies in the universe. Once that was resolved, that we had a universe filled with galaxies, possibly the next major debate that happened in cosmology was the debate between steady state and the Big Bang theory. Even though many newspapers keep claiming that some observation verifies the Big Bang theory is not under debate today in cosmologists. All cosmologists generally, almost all cosmologists generally believe it. And the main reason for it is the galaxies moving away from each other cannot be explained very easily. Well, that's the expanding universe in any other way. Because the perfect cosmological principle and the and steady state can explain it, but they had to put that in by hand. It doesn't explain it easily. Okay, so unbeknownst to the people who made the predictions of the Big Bang background, that there would be some kind of light in all directions that came from when the universe was really hot, there were people who were just doing radio observations, who were trying to map our galaxy in radio emission. And two of the most famous people doing that were Penzias and Wilson. And they had this horn, which I have a picture of here. This is the horn. I think it's in New Jersey. For some reason, I think it's in northern New Jersey. So they decided to map the galaxy and in microwaves, and they were having a good time doing it. But they found some kind of hiss in all directions. And they didn't know what this hiss was. And so they would take their radio horn that was able to hear microwaves and look in another direction, and they'd still get the hiss. And so when you see something like that, a natural first guess is that it has something to do with the equipment that you're using. If there's some kind of bad circuitry or some kind of vibration or something in your equipment, then you could generate that, and it wouldn't matter which direction you looked. You would just see it. So they kept eliminating possibilities for what it was. One of the possibilities is that there was warm pigeon poop in the horn, and this warm pigeon poop was giving off these very slight, faint hiss in microwaves. But that didn't work. They cleaned out the pigeon poop. They then published a paper saying, we see a strange hiss in all directions, which is a bold thing, because they possibly could have been laughed at. If other people were to build similar equipment that didn't have pigeons around it, and they were not able to see it, and this was coming out, and they're the only horn seeing this, and they're the only horn with pigeon poop in it, well, then it might just be they didn't clean out all the pigeon poop well enough, and they're sort of embarrassed to have published a paper on it. And they would say, oops, sorry. And then they would probably, continue on in their scientific careers, but people would be a little bit wary about their big claims. But they published it. They were bold enough to publish it, and in a very similar issue, it might have been the same issue. There was the publication, I think, by people saying, hey, we should see some kind of background radiation. Why don't people go look for it? And these people lived a few hundred kilometers apart. They could have spoken with each other, I guess, but they didn't. And so here we have, in very close proximity, was a prediction and a sort of a confirmation of that prediction. And the microwave background radiation was discovered. And very soon, relatively soon after that, Penzias and Wilson went on to win the Nobel Prize for their discovery. Okay, so again, here's the horn. So what is this microwave background radiation? Well, we're going to back up into the very early universe in this lecture. But when the universe was only 400,000 years old. Okay, so now we have to say, what do we mean by 400,000 years old? So I've given a little bit of this before, but let's go back and take the expansion of the universe, and the galaxies are all moving away from each other, and run that backwards. So if you run that movie backwards, the galaxies are all moving toward each other. And so let's keep them moving toward each other. And let's find a time when all the galaxies were all touching. They could be touching, you can think of it as a golf ball, but that doesn't really work. It could be everywhere in space-time. So it looks from any point that the galaxies are all touching you here. All the galaxies just converge on us if we run that movie backwards. But if you move to any other place in the universe, it would look the same there too. So you could think of it as all converging on lots of points, or a balloon that's deflating. So does it really mean that the universe was a point if you run this all back? And my usual answer to this is no, we don't know that. So this is just an extrapolation of the expansion of the universe back to some time which we will call arbitrarily t equal to 0. It's an extrapolation. Do we know the universe was actually at a singularity at t equals 0? And the answer is no, we don't know. We lose things at a time that I'll tell you, at the Planck time, we've lost confidence that what we know is correct. It could be the universe could have bounced. It could have never been at a singular state. It could have bounced. Any number of things. Extra dimensions could have been more important. Other things could have come in importance. So the time t equals 0, from which the Big Bang is measured from, is an abstract point in my view. And past a certain time, we lose the ability to make any meaningful predictions. So, as a physicist, I can try to make predictions as to what things would happen in this room, but I can't see what's happening right now outside this room. So if there is some ball rolling down the hallway, I don't know how fast it is. I can't make a prediction as to what's going on. So in terms of our understanding of physics fuzzes out at, as we'll see, 10 to the minus 43 seconds after this extrapolated 0 point. And we don't know what really happens before then. Knowledge always has its limits, and modern cosmology has really hit its limits then. You can get people willing to speculate what happens back then, but at this point we've lost, in my view, real physics and gone into sort of philosophy extrapolation, kind of estimations of what might have happened. To the best of my knowledge, nothing is really testable. So it's somewhat fanciful. It can be highly mathematical, but it's somewhat fanciful. It's a lot of fun, though. So people are curious as to what common speculation is about that. But I won't go too close to that in the next few lectures, the next 3 lectures. So the 4th lecture is pseudoscience of the remaining 4. Okay, so we're going to go back to 4,000 years old, which means 4,000 years after this extrapolated time. At that point, we know the universe is expanding and cooling. So things generally that expand cool. So the famous mushroom cloud that happens in explosions and even atomic explosions, that's an expansion of something that's really hot. So things that are really hot tend to expand. So the universe is really hot, and so it expanded. What did it expand into? Well, the whole thing expanded. The whole universe, usually measured by the average distance between galaxies. The average distance between galaxies, or any two things, was increasing. The strange thing was, back at 400,000 years, we didn't have galaxies yet. So you had to come up with another average distance between nucleons, maybe, like protons or neutrons, was increasing. So at that time, at 400,000 years old, the temperature of the universe was dropping, and it was at 400,000 years, it was 3,000 degrees Kelvin. Now, at that point, there was all kinds of protons and electrons bouncing around, and neutrons, and so it was a plasma. There was a lot of charged particles. Now, charged particles reflect light a lot better than neutral particles. So photons were always bouncing off these charged particles that were pretty dense. Now, suddenly, when it got cooler than 3,000 degrees, then the protons and the electrons, previously, they'd run into each other a lot. But they ran into each other so energetically that they didn't stick together. As the universe cooled, cooling is a way of saying that things are moving more slowly. As things began to move more slowly, the electrons and protons, which were attracted to each other because they're oppositely charged, they would hit each other, but they wouldn't hit each other so fast that they wouldn't stay together. So now they could stay together, and protons acquired electrons, and you had hydrogen atoms form that were neutral. So the universe became neutral. And when that happens, these photons that previously kept bouncing off of things, the photons now fly free. And the universe was able to become, well, dark. Photons flew from that hot surface to where we are today. And so we see them now as the universe expands. Again, everything cools, including the photon field cools. And the photon field cools by becoming more and more red. So even though they're not bouncing into anything, as the universe cools, the photons go from near the, well, in the X-ray range to the microwave range, where we see them today at 2.7 kelvins, which is really cold. There had been inklings before this that the universe, that there was a microwave background radiation. You can find a paper that looked at a molecular cloud. I don't know the exact citation. It looked at this molecular cloud, and there was an unusual comment in this paper that the molecular cloud appears to have one of its molecules seems to be heated up to 2.7 degrees and is not going to absolute zero. And they just brushed it off as, don't know why that would be. So many times after a major discovery is made, you can go back and look at the body of scientific data and say, yeah, if we had known that, we could have pulled this out. And so you could go back into the data and say, you know what, that molecular cloud, you know what was causing that molecular excitation to be 2.7 degrees? That was the microwave background. But back then, they didn't guess that. If they had chased that oddity, you know, and really aggressively, people who published that paper might have been the first ones to have discovered the microwave background. It was discoverable in that way, but they weren't connected to that, to that line of thinking, and I guess they weren't so bold. So now we know that this microwave background radiation, since the universe was everywhere, comes to us from everywhere. The universe is moving through this sea of radiation. Now it's not, these photons are not as dense as or energetic as the solar photon field. So most of the energy we get in light comes from the sun. And this is relatively hot stuff, hotter than 3,000 K even, because the surface of the sun that we see is, you know what, 6,000 K. And there's also the corona, which gives us some X-rays, but the X-rays don't make it to the Earth's atmosphere. So the microwaves do, and another way to see the microwave background radiation is if you have a television that has bunny ears and is not plugged into cable. So unplug the cable from your television and go to its analog signal. And I don't know exactly what channel does it, but some of the background static you receive, the noise, is actually microwave background radiation. So you've actually, I guess, so in the future people won't know about that, since in February of next year we're going to totally switch over to digital. But many people have who's had a television that's had static. So you've probably seen some fraction of microwave background radiation in the noise there. Okay, so we now know this is all around us. It's not very energetic. It's not going to heat up our coffee. We can't just hold up our coffee and let the microwave background radiation heat it up. It's very faint. That's why you need big dishes to see it. But it's everywhere in the universe, and it is profound. It comes from a very early part of the universe. Okay, so let's look. We'll get back to these 2 points here. Okay, this is a map of the microwave background radiation. So this is the plane of our galaxy here. So we generally try to take out the cosmological significance of things in the plane of our galaxy because there are things in the plane of our galaxy that emit infrared radio microwaves, and so it's a little bit confused there. So any spot like this that we see, we say, oh, look, on the microwave background, there's a strange spot. No, that's in our galaxy. This stuff, though, here, the rest of it, is quite interesting. So first detection is you see a very smooth photon field, the same kind of photons coming from all directions. But once you get a better microwave telescope, you can see that the microwave background radiation is slightly hotter in one direction than in the other direction. So let's call this one the hot direction, and this one the cool direction. Now, shouldn't we have red as hot and blue as cool? Well, no, because if you remember your black body temperatures, blue is hotter than red, even though on almost all heating devices I tend to buy, it seems to indicate that red is hot and blue is cool, but in physics, with black body radiation, blue hot is hotter than red hot. So that's the way this all sky map is colored. This is created by the COBE satellite, which orbited the Earth for many years and got the best map ever of the microwave background. And one of the crudest things it got was this map, and it showed that it's hotter in one direction than the other. And so something crude as this, surely we can understand. And there are two answers to that, is yes, we understand it, and no, we don't understand it. So the yes, we understand it is, the reason why it's hotter in one direction than the other is because we're moving. The Earth is moving around the sun, and the sun is moving around our galaxy, and that doesn't explain it. Our galaxy and M31 are moving in a local group, and our local group is falling toward the Virgo cluster, but even that doesn't explain it. Somehow, about 600 kilometers per second is unexplained, and we're moving with respect to the microwave background. So we understand that moving would create a hot spot in our direction of motion. That's relativistic aberration. So as I mentioned before, if you drive down the street really quickly, and there are two stars in front of you, those two stars will appear to move together just because you're moving quickly, and will appear more blue. And if you have two stars behind you as you're driving down the street really quickly, those two stars will appear to move apart behind you, and they will appear more red. And that's just the way relativity works. Has nothing to do with gravity. So if you look at a uniform photon field, you'll see this. You'll see a hot spot and a cold spot. So we understand the physics as to why this would work. And this matches motion. What we don't understand is why we're moving to this particular location. What's out there? When we look in this location, you might think, oh, I bet there's lots of massive stuff there that's pulling us in gravitationally. And the answer is, well, there's some massive stuff, somewhat nearby. But if we had just looked at the galaxy field, we would not have picked that spot to be the spot that we're zipping toward at 600 kilometers per second. So there's a mystery. Why there? Why are we moving toward that spot? And the answer is we still don't know for sure. There might be mass concentrations that we didn't know about. There might be large-scale flows in the universe that we're just learning more about. Okay, now that we know that we are moving, though, we can model this motion and take it off the microwave background. So we can subtract it and say, okay, we know we're moving. We don't know exactly, we know the physics. We don't know why we're moving in that direction, but we can subtract it. And so when you subtract it in the COBE maps, Cosmic Background Explorer maps, you get this. This is very dramatic, and this is one of the reasons why the COBE people, the two leading COBE people, won the Nobel Prize a few years ago. You find out that the microwave background is not completely uniform. That there are hot spots and cold spots. Let's go to a different color. Hot spots and cold spots. So hot spots are in blue, cold spots are in red again because that's the way I want it. Could have, if I wanted to, I could have flipped this in digital color, but that's not the way it was published. And so people, well, what could cause that? Why would the microwave background be? Now these hot and cold spots are very, very slight. They're 1 part in like 10 to the 6th. So these are like micro-Kelvin deviations, hard to measure, which is why you need a specialized satellite to measure this. So to a good approximation, the microwave background is 2.7 degrees in just about every direction you look. Then you have the dipole moment that you saw previously, and past that you have these hot and cold spots, which are 1 part in 10 to the 6th. But they are there, and they are significant. And so people sit around, and even before this is measured, it was predicted that something like this would be seen. People wonder, well, how could you get these hot spots? Wouldn't it be completely uniform? And the answer is no. Well, the universe was not completely uniform when it was all protons and electrons and ionized, and when it cooled, before that, it had clumps in it. It had density clumps in it. And those density clumps would have put hot spots and cold spots on the microwave background as the universe expanded and cooled. And so you can do a really cool thing and map. You can say, okay, let's say the universe was made out of all regular matter, just like we are. Then how much clumping, what kind of peaks and valleys would you expect in the microwave background due to the amount of gravitational clumping? And you can predict it, and you can look at the microwave background and see if it's the same. Now, you don't know exactly where those clumps would be, but you know statistically that you would get a whole bunch of this kind of clumps, high clumps, like maybe you would expect maybe 4 big clumps and a few small clumps. And you don't know exactly where they are, but you know the statistical nature of them. So you look and you compare what the universe would be if it was made of normal matter completely to what we see today on the microwave background. And is it a match? The answer is no. It's not a match. So you can ask, okay, let's say the universe is different geometry. We talked about geometry last time. Which geometry is best fit by the microwave background? So it turns out that the microwave background is best fit with a flat geometry that has only something like 30% gravitational matter like you and me. That's the best fit. And that is one indication that dark matter makes up the rest. Besides satellites that orbit the Earth, another way to look in the microwave is to go to the South Pole, because the South Pole has pretty clear air that microwave radiation can go through. And so this is the Dossi experiment, which got some good data also down near the South Pole. This is Boomerang, the Boomerang experiment, which also got that. They flew some balloons. So this is just artists rendering, putting that on the sky. So here's a balloon being, actually it's this long thing here, and this balloon is going to float up in the atmosphere above the South Pole. And with its detectors, I don't know, the detectors might be here, but I might have gotten it wrong. Maybe the detectors are somewhere else. Let's pretend they're here. Then those detectors would measure the microwave background in several directions and see what its statistical properties are, and that was another indication. So there was actually, about a decade ago, a tremendous race to find out what the spots in the microwave background were. There were, the Kobe satellite had said there are spots in the microwave background, and humanity, the microwave community basically came to the understanding that these spots would tell us a lot about the universe. And so everybody wanted to be the one to read off the universe in the microwave background. So there was all kinds of equipment being built at the South Pole. There were balloons being launched. There were new satellites being planned. And there was a race to read off the microwave background. Who won the race? I don't know. I wish it was really clear. Everyone won because we got a really good reading of the microwave background, and we now know a lot about the universe that we didn't know before. It's one of the things where it's not all that clear. The South Pole experiments got much of the way there. They found smaller and smaller error bars. Then a space mission was mapped after the error bars were smaller by some degree, called WMAP, the Wilkinson Microwave Anisotropy Probe. And that got even better data. It did not revolutionize things because just the previous year, there was already reasonably good data from projects like Boomerang and Dossi. But WMAP got even better data. And so it's easiest just to look at the Wilkinson microwave anisotropy map, and it's the best map we know today. And so if you notice, this picture looks a lot like this one. You see this part here? Let's go to green. You see this here, the blue spot? That's this blue spot there, see? Go back, you see this red stuff over here? That's this red stuff over there. So you notice there's many more small spots here in the WMAP sky map than in the Colby sky map. And so WMAP was able to determine a lot about the universe. And so we now know many things about the universe we didn't know before. For instance, we know that the universe is, let's go to red, it's about 13.7 billion years old. We know that omega matter is about 0.3. We know that the total omega is about 1, which means flat. So from that, we can guess that there is an omega lambda, which is dark energy, which is 0.7 about. It's controversial as to whether WMAP actually got Hubble's constant or not. To get the best answers, you have to actually put in Hubble's constant. But Hubble's constant is now known by mostly other means to be roughly about 71 or so kilometers per second per megaparsec. So in the past 10 years, the fundamental cosmological parameters of the universe have been found. So it's a tremendous change. We now know what the universe is. We know the geometry of the universe. We know gross things about the components of the universe. So it's a little bit like 1,000 years ago or so, finding out that we know now that there's air. And there's something called nitrogen, which is mostly air, and there's something called oxygen, but we don't know much about them. We now know there's mostly dark energy. There's also dark matter. There's a little bit of matter like us. Okay, so this allows us to go back into the Big Bang and understand it better than ever before. So I now zip through the Big Bang again, and we will go back to something called the Planck time. It's got a C in it because it's named for Max Planck, who was a middle-aged scientist when he quantified things and didn't quite believe it himself, but lots of things are named after him. He also had the famous quote that new paradigms in science become believed by scientists, not when a scientist gets up in front of the other scientists and convinces them of their fantastic data and logic. That usually doesn't happen, because scientists are like regular people. They're curmudgeon and destined to believe what it is they were raised to believe. The big paradigm changes in science, he said, happened when the old scientists die off, and the new scientists are all taught the new theories. So anyway, that was an aside. Due to the quantification of Planck, one can come up with a time called the Planck epoch. Before the Planck epoch, we don't know what happened. It's 10 to the minus 43 seconds after that extrapolated zero time that I talked about. Before 10 to the minus 43 seconds, we don't know. General relativity has to be too curved. Space-time breaks down. Quantum mechanics and gravity say major things about the universe at the same time, and we don't have a combined theory of quantum gravity. We know some things about what the theory of quantum gravity likely says, but just some. There are string theories that try to get into it. There's something called loop quantum gravity. There's guesses right now as to what that might be, but we don't really know. There's no series of definitive predictions that are being knocked off by telescopes around the globe. Before 10 to the minus 43 is that realm that I was talking about, which is somewhat speculation. So we'll pick the time up there. Between 10 to the minus 43 and 10 to the minus 35, as the universe expanded and cooled. Why was the universe expanding? Don't know. It just was. Cooling, because things that expand into vacuum cool. It's something called the radiation epoch dominated. So it doesn't matter what kind of particle it has. All particles are bumping into each other in this hot soup, hot dense soup. So if we were to just go there, if we were to transport ourselves to this epoch, this radiation epoch in this early universe, we would explode because we would be bombarded by this energetic stuff that would totally annihilate our bodies. And we would be broken down to our constituent subnucleons in a fraction of a second. So we can't go there, or we can extrapolate back that it existed. So we call it the radiation epoch because everything was moving fast. So even if you say, okay, no, let's make things out of protons. Yeah, that's not photons, right? That's not radiation. But it is back then. Anything is radiation because it's moving essentially at the speed of light. It's so hot that everything is moving essentially at the speed of light. And everything bangs into each other. So even if it started off not being a photon, within a fraction of a second, it's going to bang into all kinds of stuff, and it's going to be partly photon for some fraction of the time. You have this soup. You don't even have nuclei, because if you tried to form a nucleus of basically quarks, mostly what you have are quarks. If you tried to get quarks together, they would be bumped into by another quark soon enough and dissolve, and you wouldn't be able to hold into nuclei yet. Okay, so a strange thing happened at 10 to the minus 35 seconds, which is a change between when different forces become important. At between 10 to the minus 35 and 10 to the minus 32, the universe begins expanding, not as if the universe takes on a repulsive gravity field everywhere and begins expanding exponentially in what's called inflation. It's a repulsive gravity. So it's kind of strange, but this universal expansion is seen today. Well, evidence of it is seen today, we think. On the microwave background, on the horizon problem, we'll show other reasons for the inflationary epoch. But right now, just believe that most probably the universe underwent an exponential expansion between 10 to the minus 35 and 10 to the minus 32, where it became much, much, much larger. Okay, after that, inflation stopped, the universe was reheated, all kinds of quarks were then formed again, the universe kept expanding and cooling, and the universe dropped to about 10 to the 13 Kelvin, very, very hot. Another radiation epoch was created where all particles were again zipping about. Again, it was too hot for nuclei to be stable. At this point, you had, antimatter and matter existed in roughly equal quantities. But as they ran into each other and the universe cooled, eventually all the antimatter just about annihilated the matter, but there wasn't exactly the same amount of matter and antimatter. So the little bit of extra matter that survived created all the rest that remained, that became you and me. So between 10 to the minus 6 and 1 second, the universe kept expanding and cooling. Eventually, even at the temperatures of 10 to the 13, 10 to the 10, you could finally have protons and neutrons. It's cool enough for protons and neutrons to freeze in and not be broken up anymore. So, so these nuclei, protons and neutrons, well, this is actually, shouldn't have been in there, were now cool enough so nuclei could form. So nuclei are stable even past that. So what happens is, as these nuclei are stable, they keep bumping into each other and forming heavier elements. But most heavy elements can't be formed because they break apart too fast. Particularly if you have 5 nucleons or 8 nucleons, they drop off pretty quickly. So the universe is pretty much mostly hydrogen and helium at this point. Those are the nucleons that remain. So helium has 2 protons and 2 neutrons. Okay, then we reach the universe continues to expand. You have these nucleons, you have protons around. The universe continues to expand, and finally at 3000 you have what's called recombination, which I described before. This is when the protons finally acquire the electrons. So at that point you have atoms. So nuclei become atoms instead of just charged nuclei, and the photons fly free, which means that we can see those photons as the microwave background today. After that, you had essentially just a cosmos that had lots of gas in it. And it took a while for that gas to form. It took millions of years for that gas to form into things. Eventually, stars formed. Before stars formed, the universe was quite dark. And you had the background radiation, but besides that, you didn't have more sources of light. As after the dark ages were ending, you had the first stars forming. And these stars lit up the universe and even reionized the universe. The universe was again becoming less dark. Once you have the stars forming, these stars would form into galaxies, and the universe would continue to cool, eventually becoming the 3.7 degrees Kelvin that we see today, kelvins. So this is background light. This is light from the first stars. I believe this is infrared. So the gray stuff is not the first stars. Look past the gray stuff and see the clumpiness on the infrared background, that light that came from the first stars. Computer models show what the first stars might have looked like as they were forming. Here we have density contours of gas, and the first stars form in there as the gas contracts. The first stars are thought to have been much more massive than the current stars, and all have exploded relatively quickly, leaving a second generation of stars, which many second generation stars still exist today, the very low mass ones. But many of those also exploded and created third generation stars, of which our sun is one, is a third generation star. Okay, so here we see a picture of the early universe. So how do you get a picture of the early universe? Well, as you look out, the further out you look, the further back in time you're looking. So when we see the microwave background radiation, we're actually looking all the way back to 400,000 years after the Big Bang. But if we look at a galaxy, then we're just looking at a relatively nearby galaxy. So if you want to see far back in time, you want to see things that are far away and very faint. So one clever thing to do, I think that was championed early on by Tony Tyson, famous astronomer, is to look in a spot that there's nothing there. Try to take your big telescope and point it to a place where there's no bright stars, there's no bright galaxies. Find a dark spot and just burn it, in the sense of point your telescope there for hours and hours and hours. So here we have the Hubble Space Telescope was pointed, I think this is the Hubble Deep Field, HDF it's called, Hubble Deep Field, where it stared at a blank spot in space, and what it found were lots of early galaxies that were some of the first galaxies to form. And so here we have this one here, labeled number 2. Here's a blow-up of it over here. And here you see these first galaxies are lots of little galaxies falling together. So we know that although there were big things in the universe, there were lots of little things that formed, and galaxies were constantly eating other galaxies. And the early universe is just filled with lots of these small galaxies coming together. Looking at the local universe, we can see that there's all these superclusters. I think I've showed this image before. Here's the plane of our galaxy. There's all these superclusters of what has happened. So the matter has clumped now to a great degree. Here is a timeline of the universe from supposed singularity to galaxies forming to greater distances between galaxies. I'm going to speed up because I'm running low on time. Here is another graphic. So here are quantum fluctuations in the early universe. Here's inflation. Here's the dark ages. This is a really interesting map. Here's stars being formed. Here's galaxies being formed. And here you are today. And today we've entered a region where we're dominated again by dark energy. Dark energy which caused the inflation billions of years ago. We've seen this pie map before. That most of the universe is now considered to be dark energy, 70-some%. Dark matter makes up 25%. The rest of it makes up, 5%, of which most is hydrogen and helium. And the heavy elements like us are only 0.03% of the matter energy of the universe. So the Big Bang epochs can be divided into a radiation-dominated epoch, an inflationary epoch. Then we entered into the matter-dominated epoch, which instead of radiation, the attraction of radiation dominating the universe, it was matter. Even though there was dark energy in the universe, it didn't dominate. It was relatively little compared. Nowadays, though, the matter is dissipating. And so the galaxies are moving apart means the average energy density due to matter and dark matter is going down. But the energy density due to dark energy is pretty much the same. It doesn't change, we don't think. So as the matter dissipates, the dark energy is coming to dominate again. So here we see, again, here's a Hubble Deep Field again, looking between the galaxies, seeing lots of small background galaxies. And here we see another, once the Hubble Deep Field was successful, they did even more deep fields, one of them called the Hubble Ultra Deep Field. And this is a picture of the Hubble Ultra Deep Field. And in the original picture we showed in the beginning, inside these green circles are some of the earliest, most primordial galaxies ever seen. So this is what happened when stars were already formed, and these stars were then congealing into galaxies, and these galaxies were falling in toward each other. So next time I will have more about the physics of the earlier universe, and even the next lecture. So we're not done talking about the early universe yet. So we're going to get into some of the physics of what happened. We're going to talk about dark energy a lot more next time. So until then, I'll see you then.